In today's lesson, we are actually going to be looking at kind of two concepts together. We're going to be looking at theoretical versus experimental probability, and we're also going to be looking at mutual and non-mutually exclusive events. So just a review of theoretical and experimental probability. So you can take a look at the question below. You can pause the video for a second if you'd like to then quickly look at what the final answer would be, or to try to solve this on your own. But this would be a review of experimental probability. So you can take a second to try to go through and complete the following question just as a bit of review. So coming back to this question, we found the probability for each of the different ice cream flavors are based off the experimental probability from the number of sales. The only one small calculation we did have to do, we did have to calculate what the total number of cones sold was. That would be our NT, or number of trials, you might say, or the total number of cones sold. Then you just divide the number of cones for each specific flavor divided by that total to get the decimal. And then if you wanted to multiply by 100 to get the percent, you could do that as well. Now B, how will this impact Michael's order next week? Well, if we look at the probability of selling a specific flavor, he may want to stock up on that specific flavor because there's going to be chances that he's going to sell more of that one. So he's going to probably order more peanut butter and chocolate because there's a chance, or there's a higher chance of selling that compared to, say, butterscotch, where there's only around a 9.5% chance that he would sell an ice cream cone of that flavor. So you can use that kind of probability to determine which flavors he should order and maybe which ones he should not, and maybe which ones he should change. The next question, so a Spotify playlist consists of 8 rock, 12 rhythm and blues, and 4 jazz songs. If a song is chosen at random, find the probability that the one chosen is, and we're looking at rock, not jazz, and then finally, what are the odds in favor of choosing rhythm and blues? So again, pause the video to try to go through and do this review question, see what you can come up with. So coming back and looking at this question, again, we did have to calculate the total number of songs in the playlist, which there are 24. So the probability of rock is 8 over 24, or roughly 33.33%. Probability of not jazz. Now there are two ways you could have done this. You could have added up all of the outcomes that were not jazz, so the 8 rock and the 12 rhythm and blues, so 20 out of 24. Or you could have used the indirect method, found the probability of jazz, and subtracted that from 1 to find the probability of not jazz, or the complement, which again is indicated by this little apostrophe. Then what are the odds in favor of choosing rhythm and blues? So we set up our ratio, the probability of rhythm and blues to the probability of not rhythm and blues. Because we're looking at in favor, the probability of getting it should be first. Or you could look at the parts. So how many parts of our playlist are rhythm and blues? There are 12 compared to 2 parts that are not rhythm and blues, which is 12, which you could reduce to 1 to 1. So the odds are 1 to 1 in favor of choosing rhythm and blues, which works out to about 50%, or not about, it is 50%. So the odds in favor are 1 to 1. And if we wanted to look at a probability, which is a different question, it would be a 50% chance that we chose rhythm and blues. So that was a bit of a review on theoretical and experimental probability, which is what we looked at in the last 2 lessons. We're just going to look at comparing the two now. So the theoretical and the experimental. So theoretical probability, it is the probability of an event occurring based on the set of possible outcomes. Short of it is what should happen, right? So theoretically, based on all the possible outcomes, what should happen is your theoretical probability. The experimental probability, while calculating it is the same, it's defined as the probability of an event occurring based on what has happened in the past or by experiment. So it's different because it's what did happen. So theoretical is what should happen, experimental is what did happen. Right? So calculating it is the same, but what the meaning is a little bit different, and the values can vary. So for example, if we look at a simple scenario, flipping a single coin. So what is the probability of flipping a head? Well, the probability of heads, there's one option out of two, so 1 out of 2 or 50%. For probability of getting tails, again, 1 out of 2 or 50%. There's one tail on the coin out of 2 possible options. So if we were to flip a coin, what are the outcomes? And then what about 1,000 times? What are the outcomes? So if we bring up a random generator or flipping a coin, let's toss 10 coins and see what we get. All right, so we've tossed 10 coins. From our simulator, we found that we get 7 heads and we get 3 tails. So looking at that, well, that doesn't quite fit our scenario, right? That doesn't fit our probability. It should be 50-50, 50% heads, 50% tails. Now, the difference is the 50-50, the 50% for each that we just looked at, that was theoretical. That's what should happen. What we just did here, we did an experiment. So we ran some trials or ran some tests in our experiment, and we found that the experimental probability is different. Now, the next part of that is what would happen if we did 1,000 trials? Here we do 200 trials. Let it just run its course. Do another 200 trials. What's happening to our probabilities? You can take a look at the graph to see it. You can take a look at the bar. So we're at 400. Let it run its course again and just take a look at what's happening. You can take a look at the numbers, take a look at the bar, take a look at the graph. 600. So now let's do 800 and then one more for 1,000. And again, look at what's happening to the outcomes. What are we seeing? The line graph is a nice visual to kind of see it, how it's changed over time. And for our last one, to do 1,000, again, what's happening? So we've run it 1,000 times, and for heads, we got 518 out of 1,000, or 51.8. And then for tails, we had 482, or 48.2%. So what did we notice between the two? Coming back, what did we notice between the two different scenarios? We flipped it 10 times, 70% heads, 30% tails. Flipped it 1,000 times, 51.8% heads, 48.2% tails. So what do we notice? And what you should notice, and it does appear a lot easier when we look at this graph here, right? Seeing how the probability or proportion of heads changes drastically at first, and then over time, it almost becomes a straight line at about 50%, which is what we were expecting. So what do we notice? Well, the more trials we do, the more trials in our experiment, the closer the experimental gets to the theoretical. So neither probabilities are wrong, the theoretical or the experimental. The only reason why there might be a difference is because we haven't done enough trials. Because again, theoretical is what should happen, experimental is what did happen. If we only do one trial, it may not work out like that. But the idea is that the more trials we run, in this case 1,000, if we did it more to 1,000,000, right, 1,000,000 times flipping a coin, Right? The idea is the more and more trials we do, the closer the experimental will get to the theoretical. So we'll get closer to what should happen. And that's what's called the law of large numbers. So the law of large numbers is basically just stating that as more trials in an experiment are completed, the results should be close to the expected value or outcome or that theoretical. So the more trials that you complete, the experimental probability will change and get closer to the theoretical probability. So we can revisit that Monty Hall problem that we did in an investigation earlier, where our outcomes didn't really match what should happen, right? And you might be thinking, well, I'm going to stick on the door that I picked because in my 10 rounds, that's what I did better at. I got more cars. Or you might say, well, I'm not going to choose the switch option because I switched and I didn't win. The idea is, though, if you were to be on that game show, say for 100 times, the chances of you winning by switching should be a lot higher than if you were to just stay with the door. So the idea is you look at a large sample size, large number of trials, switching is the best option. Now, obviously, in the moment, if you only get one opportunity, you still want to switch, but that may not mean that you actually win. So again, you can't always rely and say, well, the theoretical is, so that's what's going to happen. It's what should happen, but it may not. Right? If you were to do it over and over again, yes, then it should. So moving on from that, we're going to look at some different scenarios that we may come up with when we're looking at probability. And the first one is mutually exclusive and non-mutually exclusive. So first, mutually exclusive. Mutually exclusive events are events that cannot happen at the same time. So the events or the outcomes are two separate things. So for example, right and left-hand turns. You can't take both at the same time. Even in odd numbers on a die, right? So if you roll a die, it's only going to be even or odd. It can't be both. Winning and losing a game. You can't win a game and also lose a game, right? So it's two separate events that cannot happen at the same time. Down here, we see kind of a sample space. So this is an example where aces and kings are separate, right? Those are outcomes or events that cannot happen at the same time. I can't pull a card and have it be an ace and a king. So let's look at some examples. So how many cards are clubs? Well, clubs are one suit, so we have 13 cards that are clubs. So for B, what is the probability of drawing clubs? Well, of drawing clubs, we have 13 cards out of a total of 52, or 1/4, or 25%. So 25% chance of drawing clubs. What about the probability of drawing spades? Well, spades are also a suit. So there would be 13 cards out of 52, or 1/4, or 25%. Now for D, what is the probability of drawing clubs or spades? Well, in that case, you might be able to think of the answer right away, but let's look at a sample space. So in our sample space, the total number of cards should equal 52. In the two circles, those are going to be my two events. So I'm going to have clubs in one, spades in the other. There are 13 cards here, 13 cards here, and then outside of those two events, there are going to be 26 remaining cards, right? The hearts and the diamonds. So if I look at the probability of drawing clubs or spades, I have 13 clubs, and 13 spades that I could also pull, over 52 total options, which gives me 26 over 52, or 50%. So there's a 50% chance that I draw a club or a spade. So when we're dealing with two mutually exclusive events, we use what is called the additive principle or the rule of sum for mutually exclusive events. And that is basically saying that the probability of either two mutually exclusive events, A or B, is, and here we have our formula, the probability of A or, so this symbol just means union, so A union B, which means A or B. So the key thing, just write it a little bit bigger, union, or, so the key word is or. That's what you're going to be seeing a lot in questions. So when we have A or B, then the probability is just the two events added together. So that's when they're mutually exclusive. So for example, a cooler contains 3 orange, 5 apple, 3 citrus, and 4 grape juice bottles. What is the probability of randomly choosing an apple or a grape juice bottle? So in this case, if we look at our sample space that's already drawn for us, apple there's 5, grape juice there's 4, and there's 6 remaining ones. In total, we have 15 juice bottles. So the probability of apple or grape, so you can use that union symbol, or you can just say A or G. However you want to word it is up to you, or your formulas is up to you. A or G is fine. We're looking at the probability of getting an apple plus the probability of getting a grape. So in this case, 5 out of 15 plus 4 out of 15, which equals 9 out of 15. We can then convert that to a decimal of 0.6 or 60%. So there's a 60% chance that we are pulling a apple or a grape juice bottle. And again, we see that in the question, or, right? So that should tell us that we have to add. So that's one of those keywords that we should be looking for when we have our questions. So if we look at non-mutually exclusive events now, so non-mutually exclusive events are different. So this is where these are events that can happen at the same time. So the non-mutually mutually exclusive, they are exclusive, they cannot happen at the same time. Non-mutually exclusive, just basically saying the opposite, they can happen at the same time. So driving and listening to the radio, you can do both of those at the same time. Even numbers and prime numbers on a die, right? So you can roll an even number, which is also a prime number. Losing a game and scoring, so you can lose a game and score at the same time. If we look at an example sample space, looking at a deck of cards, right, we can have hearts as one outcome, kings as another outcome, and there is one scenario where they happen at the same time, where you have a king of hearts, which is both. So that's the difference. We're looking at events that now can happen at the same time. So let's look at a quick example, looking at cards. So how many cards are diamonds? Well, it's a suit, so there are 13. What's the probability of drawing diamonds? So same as before, 13 out of 52, which is 1/4 or 25%. How many face cards are there? Well, there's 3 face cards, Jack, Queen, King for 4 suits, so there are 12 face cards. Now for D, what is the probability of drawing a face card? So the probability of drawing a face card would be 12 out of 52. Which is 23.1% rounded. Now E is asking, what is the probability of drawing diamonds or face cards. So the or should be in a signal of, okay, we probably should be adding something. Now, you may come up with an answer. You may think, oh, well, 13 and 12. Let's take a look at a sample space first. 52 total cards. We're looking at diamonds and face cards. How many diamonds? Well, we have our ace. We have our 13 cards. We have our 12 face cards. However, when we visualize it, there is a bit of overlap, right? Because there are some diamonds that are also face cards, right? And not all face cards are diamonds, but some of them are, right? Because we have our jack, our queen, and our king. So then out of all those face cards, out of those 12, there are 9 that are not diamonds. There are the 3 that are, so they're in that overlap. And of all of our diamonds, there are 13 diamonds. There are 3 that are in the overlap, and there are 10 that are not. So when we look at this, there actually, if we look at it, there's actually 19, there's 22 outcomes that we could have. So the probability of a diamond or a face card is equal to not 13 plus 12, but 10 plus 3 plus 9 out of 52. So those are all those outcomes. Which is approximately 42.31%. So it's not the same as what we did in the last example with the mutually exclusive. There's something different that we have to take into consideration here. And now you may not want, it may help to draw the visual, which we'll look at in a further lesson with these Venn diagrams. But there is a way that we can do it without kind of drawing the visual. But it does require us to think about all the possible outcomes. So when we're dealing with two non-mutually exclusive events, we're going to use a formula that's called the principle of inclusion and exclusion. So when we're looking at the probability of either of two non-mutually exclusive events, A or B, so again, it's still that or, the probability of A, again, this U represents union, so A or B, so when we're looking at two events, see it as or, it's the probability of A plus the probability of B minus the probability of A intersection with B. So this N looking symbol just means intersection or and. So the probability of A plus the probability of B minus the probability of A and B. So basically what this is doing, you're removing the overlap or you're removing the double count. If we go back to that last question looking at the cards, if I just added the two probabilities together, right? The probability of a face card or a diamond, the probability of a diamond was 13 out of 52. If we add then the probability of face card, 12 out of 52, this would give us 25 out of 52. However, that's not correct because we've double counted. In the face cards or the diamonds, we've counted that Jack, Queen, King of diamonds. We've also recounted that Jack, Queen, King in the face cards. So we need to remove that overlap. So there's 3 cards that are both diamonds and face cards. So that's where we have to subtract. Now again, visually with the Venn diagram, it's easy to see. So if that helps, you're more than welcome to do that. If you prefer the formula, you'd have to think about, okay, what are the overlap sections? What are the scenarios where it's both events? And you have to remove that so that we don't double count. So looking at an example, there are 30 students in class. 10 play basketball, 15 play volleyball, and 7 play both sports. What is the probability that a student chosen at random plays basketball or volleyball? So we want to make sure that we visualize this because it might be a little bit tricky. We can use the formula as well. But there are 30 students in total in our sample space. We have basketball, we have volleyball, and there's an overlap. So we know that 7 play both. So then that means out of the 10 that play basketball, 7 play both. So there's only 3 that play just basketball. That means there are then 8 that play only volleyball, because there's 7 that play both, or 7 play volleyball in total, or sorry, no, 7 play that play both, 15 that play volleyball, so that means there's 8 that only play volleyball. That means there are 12 left over. So now we can apply our formula. We could do this without the Venn diagram, right? So there's one way the probability of basketball or volleyball is the probability of basketball plus the probability of volleyball minus the probability of basketball and volleyball. So we have 15 out of 30 plus 10 out of 30 plus 15 out of 30 minus 7 out of 30, that overlap, which gives us 18 out of 30, or 60%, or 0.6. You could also use the Venn diagram to help, because you can just say then, okay, well, the probability of basketball or volleyball, we add up all the possible outcomes, so 3 plus 7 plus 8 over 30, which gives us the 18 over 30. So depending on how you want to visualize it, either way will work. So next example. So given a standard deck of cards, right, so we have all the outcomes here, what is the probability, or determine the probability, of randomly selecting a club or a heart? So are these events mutually exclusive? Are they separate? Can I draw 2 circles and say that they're separate in our sample space? In this case, yes. Yes, they are, because a club, there's 13 of them. They are different suits from hearts, which there's also 13 of. There's 26 remaining other cards outside of those two events. So the probability of a club or a heart is equal to the probability of a club plus the probability of a heart. 13 out of 52 plus 13 out of 52 equals 26 out of 52, or 0.5, or 50%. Determine the probability of randomly selecting a diamond or a face card. So are these events mutually exclusive? Is a diamond exclusive from being a face card? No, it is not. And we kind of went through this again just previously, so no, it's not. If we were to draw a Venn diagram, they would be together. So face cards and a diamond. Similar to the example we just did, there's 3 that overlap. So there's 10 diamonds, 9 face cards. The probability of a diamond or a face card is equal to probability of a diamond plus probability of a face card minus the probability of a diamond and a face card. So you could do it in different ways. So 13 out of 52 plus 12 out of 52 minus 3 out of 52 would give you 13, 15, no, 12 minus 3, so 22 out of 52. I think this might be the exact same question that we just kind of looked at, but it doesn't hurt to review. Which equals 42.31%. Next, determine the probability of not randomly selecting an ace or a spade. So of not selecting an ace or a spade. Probability of not doing that. Right, so here it might be easier. You could think of all the ways of, so probability of not selecting an ace or a spade. You could think about doing the inverse. Right? So you could do 1 minus the probability of selecting an ace or a spade. So in this case, 1 minus ace or a spade. So probability of an ace plus the probability of a spade minus the probability of an ace and a spade. So 1 minus 4 over 52 plus spade is 13 over 52 minus the overlap where there's 1 out of 52. So in this case, 4 plus 13 minus 1. So 1 minus 16 over 52, which gives us 1 minus 16 over 52 gives us 0.6923. So 69.23% chance of not selecting an ace or a spade, which means then that there would be a 30.77% chance of selecting an ace or a spade. So again, there are some homework questions. The main idea of this lesson is, one, understanding how theoretical probability and experimental probability relate to each other, and two, looking at mutually exclusive and non-mutually exclusive events and learning about how to, or understanding about how to calculate the probability for those. Right? So one, we can just add probabilities together. The other, we have to take care of the overlap so that we don't double count. So again, just make sure you're going through the practice questions to review those concepts.